The Stoa is a digital campfire where we cohere in dialogue about what matters most at the knife's edge of what's happening now.
All right, everyone. Welcome to the Stoa. I'm Peter Lindbergh, the steward of the Stoa, and the Stoa is a place for us to cohere and dialogue about what matters most at the knife's edge of this very moment. And today is one of our first communal podcasts, something in our communal podcast series, where the Stoa is lent out, if you will, and two regular co-hosts team up and interview people at the Stoa, or have conversations, or what we like to call here dialogos. And this series is quite exciting. There's a lot of buzz around it because the guest lineup is hype. Let's put it that way. It's pretty amazing. And it's Body and Soul, the Mind of Culture. And double Gregg Thomas and Gregg Henriques, two past Stoa friends of the Stoa and past guests. And so this is session number 1, and I'm going to tag in Gregg in a moment. He'll introduce the series and then the guests today. And this is a 5-part series, scrapping on Mondays, mostly at 5:30 p.m. Eastern time. There's one happening on the 15th at 12 p.m. And that one's with, I think, Nora Bateson and Diane Musha Hamilton. So how today's going to work, it's going to be roughly a 90-minute session. There's going to be, after Gregg's intro, there's going to be a 4-way conversation. Then we're going to pivot to Q&A, so standard Stoa style. If you have questions anytime, just throw them in the chat. And then when we come to that, I'll call on you, unmute yourself, ask your question. If you don't want to be on YouTube, just indicate that in the chat, and then I will read your question on your behalf. So that being said, Gregg, I will tag you in, my friend. And I don't know which Gregg I meant there. I just,
Okay, I'll take it. Thank you, Peter. I definitely appreciate you inviting Gregg Henriques and myself to the Stoa for this interdisciplinary conversation. From matter to life to mind to culture is the name of today's. And it's the first of the 5-part series that you mentioned, which is Body and Soul, the Mind of Culture. And it happened to be John Coltrane's classic version of the song, the classic Body and Soul, that you were listening to as you came in. I'm Gregg Thomas, and I'm happy to introduce the co-creator and co-facilitator of this series, Dr. Gregg Henriques, someone who is no stranger to the Stoa.
Oh, thank you so much, my friend. Peter, thank you so much. It's really fantastic to be here. I am jazzed to be working with my dear friend, Gregg Thomas. And thank you so much for putting your leadership stamp on this. It's been great to see it come together. So I'm a professor of psychology at James Madison University. And I've been on a lot of panel discussions, as part of my career, been in academia a long time. I've never been on a panel discussion with a scholar from culture and two fellow professors, one of evolutionary biology, Brandon Ogbunu at Yale University, and Stephon Alexander at Brown. So I think it's super cool to be hanging with an evolutionary biological professor and a physics professor. So I'm really psyched. So Brandon, maybe you can introduce yourself to the crowd, just say hi, and then we'll move it over to Stephon. You got to unmute yourself there, friend.
So firstly, hi. Hello, everyone. Yeah, you heard that. My name is Brandon. I'm an assistant professor. And, I study evolutionary biology, and I study mathematical biology, and there's a lot of kind of intersections between what I do scientifically and some of my other personal interests, where I actually think and have a lot of these conversations in my head, right, about the intersection between society and science. And I'm good friends with Professor Alexander, who's been a mentor for me in that circle.
And let me ask you this, Brandon, is the correct way to pronounce your last name Ogbunu?
Ogbunu.
No.
Yeah, the G is
Ogbunu.
Yeah.
Ogbunu. Okay.
Mm-hmm. Sorry about that, friend.
No problem.
You ain't the first one to make that mistake. Okay, Stephon Alexander, unmute yourself.
I like to unmute myself. You mean like, hello everybody. I'm Stephon Alexander. Um, it's a great pleasure to be here amongst colleagues and friends, old and new. Um, and it's good to see how, first, for a disclosure is I'm the author of a book called The Jazz of Physics, and Gregg that's how we first met many years ago, where he played a pivotal role in making sure that that I had my jazz chops in the book and the history and all of that stuff correct, so that people didn't slice my head off once the book came out. So so I'm a professor of physics at Brown University, and I refer to him as Professor Brandon, my colleague at Yale. We go way back as well, and as much as he's been a mentor, I've been a mentor to him. He's also been a mentor of mine. Brandon was, just another thing is I have another book coming out, Fear of a Black Universe, and Brandon played a very key role in the initial, sort of conceptualization and bringing to reality that book. So I'm excited about who's going to chop my head off with that book. But anyway, I work at the interface of early universe cosmology, how it connects to the contemporary universe, and questions around that, and our fundamental theories of physics and what it can say to inform unknown things about the physical and beyond. So look forward to this conversation.
So Stephon, I think why don't we do it in the order of the title of this session. We'll start with matter and physics. We'll go on to life and evolutionary biology, then to psychology with Gregg Henriques, and then culture to me. So we're going to start with you, Stephon. And why don't you just take it away? Now, there is a video that we wanted to share with folks. Should we play that first, or would you like to share your slides first? It's totally up to you.
Let's start with that video first. I think that's a very impressive video. Yeah. Okay.
All right. So I think it'll be self-explanatory. This is, say, a brilliant young lady who lives in Canada. Of course, Peter's proud of that. And she won a prize for the very video that you're about to see.
So I was watching my brother play this video game, and he used a cheat code that let his character do a walk through walls hack. He pushed himself against a barrier in the game, hit some buttons, and boom, his character appeared on the other side. Imagine if you could walk through walls in real life. And it turns out you can, at a quantum level. We're talking on a scale of the stuff that make up atoms. Strange things happen at a quantum level. For one thing, all subatomic particles, they've got split personalities. One personality is a wave and the other one's a particle, but there's still one being. When you want to know where they are, they seem like a particle, and when you want to know what they're doing, they behave like waves. But you can't ask both personalities at the same time. Basically, they've got some serious commitment issues, and that means we can only guess where they might be. Imagine an electron has 2 dice, 6 sides each. What the electron rolls is where it will sit along the line. Our electron can't commit to a position until the dice are rolled, remember? Serious commitment issues. So as our electron is shaking the dice, it's everywhere at once. Something, like us trying to measure its position, has to force the electron to let go of the dice and pick a spot. Of all combinations, getting a 7 is more likely than 2 or 12. In reality, though, the electron can be in more than just 10 spots, since there are many more combinations than just 2 dice. Now we can picture subatomic particles as this, a probability wave. This wave will tell us the odds of finding a particle at that location. Say this is our electron's probability wave. The peaks of the wave is where we're most likely to find the electron, and in the valleys, it's less likely we find it there. Let's say the electron is heading towards a barrier. As it hits the barrier, the wave bounces off. But let me tell you something about waves. They are not perfect. For example, a beam of light doesn't perfectly reflect off of a surface. A small fraction of light can get through. Waves won't bounce off perfectly, so neither will the electron wave. Sometimes the wave can slip through the barrier. When the wave is in the barrier, the chances of finding an electron there goes down by a lot. But if the barrier is thin enough, the wave can reach the other side before it dies off. So what does that mean? Remember, the wave tells us how likely it is to find the electron there. This means there's a chance we can find our electron on the other side of the barrier. Or in there too. Once it's on the other side, we can say the electron tunneled through the barrier. This is quantum tunneling, and that's how subatomic particles can walk through walls. Okay, so little elementary particles can walk through walls, but I can't, because my body's made up of more than a quadrillion of these quantum objects, and the odds of all of them tunneling through the wall is practically impossible. So why does quantum tunneling even matter? It's the reason we're alive. Quantum tunneling allows nuclear fusion. Sounds familiar? That's how our sun releases huge amounts of energy that makes life on our planet possible. So how can you quantum tunnel at home? You already are. It's one of the ways our DNA mutates, among other roles that quantum physics plays in our biology. Quantum physics makes it seem like the world is playing cheat codes on us, but it isn't. It's how the universe works. Maybe the quantum world is telling us that when faced with an obstacle, there's a small chance we can defy expectations and reach barriers.
That won a prize from Sal Khan of Khan Academy, and it was well deserved. Professor Alexander.
Well, as I was watching it, I do have a section in my kind of physics. We have at Brown a physics for poet, but actually is where the undergraduates they take this, and I'm thinking to myself, she's done a better job at explaining quantum mechanics to that group. I'm gonna have to use that video. So yeah, that was fantastic, and you know, I hope she ends up in my PhD program one day. Yeah.
So what would you like to share with us, sir?
Yeah, so now what I'm going to do is in the spirit of getting everybody on the same page, at least so that we can you know, bootstrap a nice conversation discussion amongst Professor Brandon and Professor Gregg and us all. I want to kind of provide a framework as to where I'm coming from, okay? And that will be a conversation around some aspects of music, and especially improvisational music, and the cosmos and the functioning of the universe. And basically what I'm going to try to do is to kind of say a few fundamental things about our universe and how it functions. And the functioning here, we're talking about structure, meaning the structure in the universe. What I mean by that is, as that young woman said, much of what the universe has done and is doing is to make stars. So if I say I have an early universe, how early? You know, roughly 13.8 billion years ago in the past, where its you know, structure was very different from what it is today. Like, you know, which is basically a lot of empty space, and in between that empty space, lots of stars, you know, configured in pancake-like galaxies. In the early universe, it was completely different situation. It was not a lot of empty space in between, but the universe being filled with a plasma, basically very hot and energetic elementary particles in a quantum super radiation with no space in between them. And so how did that situation come to be the structure, meaning stars that's burning light and, you know, giving life energy to some planets, or at least ours at the very least. How did it get from there to there? And kind of where I want to go with that is to show some resonance between how we understand music to work and the universe, with an eye towards maybe taking that analogy a little bit further and maybe something to put on the table when we all talk together. So let me just kind of begin with, you know, again, a few slides, and I'm just going to kind of move through them kind of swiftly because I don't want to put people to sleep. Let me just find the okay, I do have it. Wow, so far so good. All right, now, so I made some little thing, and can y'all see?
You should make it as big as you can.
Okay, I'm going to enter full screen with this thing.
Yeah. Okay. Cool.
Y'all see? What? Tell me what you see there, because it's hard for me to know.
Your book, The Jazz of Physics, and then From Hip Hop to the Cosmos on the right.
Okay, good. So this is, you know, a lot of the material here is from my book, The Jazz of Physics. So I go into 300 pages of, you know, full glory in a way that I hope can speak to a general public audience with no background in physics. So now let me see. So the first thing I want to show everyone here is, you know, it's really fitting that we began with John Coltrane. What a lot of people don't know, and including myself, who is a very serious lifelong student or disciple of John Coltrane, there's a whole, like a whole school. I don't know, many people who listen to sax players. There are a lot of people out there who are referred to as post-Coltrane saxophonists. So these are literally, there are professional jazz musicians literally who will memorize Coltrane's music and study. basically devote their lives to studying and playing like Coltrane. Okay, there are people on the planet who are what we call post-Coltrane people. One of my favorite sax players is a guy named Jerry Bergonzi, who is a proud post-Coltrane player. All right, so I am a post-Coltrane scholar myself, although I don't have the time to practice like all these other cats. One of the places, though, I do enter is Coltrane's fascination with, so it begins with David Amram. David Amram was the first, Hal Bernstein made Amram the first composer of the New York Philharmonic Orchestra. He was a multi-instrumentalist. He also was the first person to introduce the French horn into jazz and played with Dizzy Gillespie. So he was one of these cats that was very hip to the classical music and jazz music. And he told me a story. I finally met him. He was in his mid 80s at the time, but very, very sharp, and he was still playing. And I had I met him one night, and I asked him about what could he tell me about Coltrane, and he told me the following story. By the way, this is intended to be roughly 10 minutes, okay? Gregg, is that fine?
That's fine. Go ahead. Mm-hmm.
So the story goes that Coltrane basically used Amram, since Amram was a composer, classically trained composer. Coltrane basically was to nerd out with Amram, and basically whenever they had a chance, they would just talk theory, like music theory, and Coltrane would just throw all these new ideas at him. So, and Amram said that whenever Coltrane would say something, he knew that what that meant was that he would throw it back at Coltrane. So Coltrane asked Amram there was a jazz club called Cafe Bohemia in the village somewhere. It's no longer with it, but he was playing with Dizzy Gillespie, and there was an intermission, and he came outside and he said Coltrane was having a pie, eating some pie, and then they started talking. And Coltrane goes, "What do you think about Amram? What do you think about Albert Einstein?" With a very serious look on his face. And so Amram said he knew what he had to say was, "What do you think about Albert Einstein?" Right? And then Amram told me that he just went off. He goes, "Well, I read his theory of special relativity, and also read about general relativity, and everything I could get my hands on, I read, and I heard about the solution of the black hole." And so Coltrane basically was a big ravaging Einstein fan, and he also got what Einstein was really trying to do. And he told Amram the system that Einstein was applying to understand the space-time structure, which is a system of what we call invariance. He wanted to do the same thing for music. Now, you have to understand that when Coltrane is telling this to other musicians, they would probably think he's insane. But when I heard that as a physicist, as a person whose professional research is based on extended Einstein's theory, I totally understood what this diagram meant. This diagram was this is a hand-drawn diagram that John Coltrane made and gave it as a present, a birthday present to Yusuf Lateef, I believe in 1961. The Lateef estate, Aisha, his wife, gave me permission for the first time to allow this to be published on an outside source. Thank you, Aisha. And she knew that this was something that Dr. Lateef would be pleased about, because the point was that this diagram, when I looked at this diagram, I totally understood that what Coltrane was doing, even though it was mysterious to a lot of jazz musicians, was exactly invoking the symmetry principle of general relativity. So if you look at this diagram, what you'll probably see are symmetric patterns. I can't go into this in detail, but in chapter 18 of my book, The Jazz of Physics, I go into this in detail and relate how this musical system that Coltrane wrote down, these patterns, are related to symmetries maybe found in the quantum theory of gravity, which is now our final quest to unify quantum physics with general relativity. The point here is, as Gregg will then talk about culture later on, is that, when we think about a music like jazz music, or music or discoveries that come from, in this case, from African Americans, the point of my book was to show that, yes, at one level, jazz is a cultural expression, a way that musicians would get on stage and perform, performative art, a form of maybe entertainment. But artists like John Coltrane and Charlie and Miles Davis, they were, and Wayne Shorter, to name a few, they were also engaged in this highly intellectual, as well as spiritual, but also intellectual pursuit to also understand reality. And it's kind of interesting that what this diagram did for me as a researcher at the time at Stanford University, it really inspired me to dig deeper into my own research in quantum gravity. So moving forward, I want to now give the audience a kind of little, some tools so that when we talk about, further talk about the universe and physics and music, there is one glue that kind of brings everything together. And that is basically that at the end of the day, when we're talking about music, any kind of music, right? The genetic code, stealing words from Brandon, right? The genome of that is sound waves, vibrations, okay? And so any medium that vibrates that can carry sound waves, all right? So the air in front of us can carry waves. And what we're looking at here is on the left of my panel here, it's what it says right below A, or what we call special types of waves we call periodic waves. These are waves that perfectly reproduce themselves. As you see, they just go up and down and completely repeat that pattern, sometimes indefinitely or as long as you'd like it to. And what we're looking at here is a very important phenomenon, which is if I take two waves here, imagine like two waves coming towards each other in an ocean, and they're perfectly aligned. And that's a fancy word. We mean that they're in phase, meaning that they rock up and down at the same rate and at the same time, such that they coincide, that when these waves hit each other or they collide, these waves will basically do exactly as our intuition tells us, which is the wave will grow in height at twice the amount if the two waves were copies of each other. Another thing you'll realize is that the frequency or the amount of time the wave wiggles up and down, the frequency will remain the same if the frequencies here were identical. That's what we call constructive interference or in phase, fancy words for just saying two like waves, when they add up to, when they hit each other, they add up together, okay? But now we have another kind of idea here. And so to give you some motivation, I gave the same lecture, hour-long version of this at Google headquarters, and it was aired to about 70,000 of Google's engineers. And so I made the following claim. I said, what I'm gonna tell you here is probably the most important idea in engineering and science, in the physical sciences, and nobody disagreed with me there, none of the engineers. And this is the idea I'm showing you. It's called a Fourier transform. Again, a fancy idea that says that, I'll summarize that in a second. And the second idea, the second piece to this concept is, so the first piece is like waves, when they add in phase, they add up constructively. And also, if I have like waves, but they are out of phase, meaning that where one wave is up, the other wave is down, so on and so forth, when they add together, they can cancel each other out. And many of us as kids playing at the beach or the pool or wherever you had access to water as a kid, we see this, we can grok this intuitively. So when like waves add up, they can add up constructively, and then if they're out of phase, they can do the opposite. But now let's go to a more interesting situation, and this is at the heart of the idea of the Fourier transform. To the right of this panel, now what I'm going to do is add three waves, and these are three perfectly periodic waves. One up here. Could you see my cursor as it moves, by the way?
Yes.
All right. So right here, this wave is fatter and longer. Its wavelength is longer. The wavelength here is shorter, and the wavelength here is in between. Now, unlike these two simple situations, if I add these waves together, turns out that I'll get a more complicated wave. And it's a very important thing. So now, I'm ready to state the idea of the Fourier transform in signal processing, or in how instruments function, which is a vibrating body that can produce a very complicated wave or signal, right? I can create a complicated wave by adding up simple waves. The same way that if I have different letters, right, in my alphabet, think of each letter. Think of each letter as a building block of a wave, right, of different frequencies that they can be added together to make a word, and that word would be a complicated word or a complicated wave. But that's not what's cool here. It turns out that when we look for extraterrestrial life, we're looking at really complicated signals from outer space. When our cell phone is now transmitting a song from Spotify, how does it do that? It does the opposite, actually. it takes a complicated signal and it can decompose it into simple basic building blocks. And that is at the heart of now we have the tools to move forward. So now what I'm going to use these tools, and oh, by the way, these tools, just to let y'all know, that in the 80s, I grew up in the Bronx, so did Brandon. And basically, it turns out that that hip hop producers, we're looking at Dr. Dre there and Jay Dilla, but people like Jazzy J and so on and so forth, were real revolutionaries and innovators because they were using digital samplers, which exactly, if you look at the electronics of a digital sampler, is the MPC 2000, which was used by both Jay Dilla and you see Dr. Dre's MPC 2000 there, where he made mega millions on using this digital sampler, uses exactly the same idea in the Fourier transform. But also, this is nothing new. We're looking at here is an archetypical picture of a musical wind instrument. And it so turns out that the notes from, if I look at the lowest note and the octave, which is a division in half, and also the perfect fifth, and all these notes are nothing more than simple periodic waves from this Fourier series idea. So in other words, what I'm telling you is that the musical scale that we use in the West is nothing more than a realization of these Fourier waves, these simple decomposition of waves. So what's this all about? Why am I saying this? Well, it turns out that we now know in modern physics that all of the basic building blocks in nature are things called quantum fields, and all the matter, the electron, the photon, the field of light, right? All the elementary are nothing more than vibrations, harmonic vibrations of these fields, the same way musical notes happen. Even though the medium is different, the patterns are very similar. And so, I want to kind of like show you that this is nothing new. This kind of musical thinking was used to actually derive the very first laws of motion mathematically. And what we're looking at here was Johannes Kepler in the 1600s, who actually figured out the elliptical orbit of all the planets, the Keplerian orbits, by first writing down musical notes associated with the velocity of the planets. Was measured by Tycho Brahe. And what we're looking at here is a picture of what we call a large-scale structure of the universe. So this looks at the largest distance scales we can imagine. I showed this picture to a friend of mine who is a professor of neuroscience at Princeton without telling him what the picture was. And he goes, "Those are some really nice neurons you got here." Okay. This is actually a picture of the network of galaxies in our universe. So what we're seeing here, every dot, if I zoom in here and I zoom out and I continue zooming in, every dot here corresponds to a galaxy like our own Milky Way. And what we're looking at here are billions of galaxies stretching across billions of light years. So to give you a sense of a scale, if this dot corresponds to a cluster of galaxies like our Milky Way galaxy, it turns out that about 1 light year is about 10 trillion miles. So you're looking at 35 million trillion, right, light years. So it is unfathomably large. But when you even look at that scale, we see wave-like patterns. And we can say as physicists, why do we see these wave-like patterns? And so let me just kind of cut to the chase. Then what cosmologists can do is look even further in the past. That's right. It takes light a finite amount of time to travel. So we can look at the light that took 14 billion years to travel to us. And this is what we see. And this looks like complete gobbledygook to us. But what if I tell you that you can use this Fourier idea? As I said, the lesson is look at a complicated signal that doesn't seem to have and make much sense and try to decompose it into waves. So that's exactly what cosmologists did that won 2 Nobel Prizes, by the way, for this work. They decompose this complicated signal, albeit in 3 dimensions. There's a projection of 3 dimensions. We're looking at the sky, the night sky, the furthest distant. Imagine you're a chicken in an eggshell and you're looking at every single direction in the universe. And this is what they find. They find that the universe in the early stages is nothing more than a sound wave pattern. And what we're looking at here in the red curve is a theoretical prediction of the waves from Einstein's theory of curved space-time, because back then the universe is an expanding system that's undergoing undulations in its vibration, which have to do with sound waves. And the black dots is the data that the space satellite took of this picture. And you can say, well, so what? Well, let's compare this to actually what an instrument does when it plays a note. And it's not the identical thing, but basically what we see now is that the universe is functioning at the largest scale as basically a very kind of simple instrument, where the different realizations of the wavelength of the peaks of these waves. So this big one here is the vibration of the universe as if it's an instrument vibrating at the fundamental frequency. And these other peaks have to do with the material makeup of the universe. If the universe is, like, for example, the flute here, if it's metallic, it's probably will be vibrating at a frequency that's vibrating at the metallic frequency of what it's made up of. And from this, we can actually deduce the material makeup of the universe, how much photons it has, how much dark matter, and how much electrons it has and neutrinos. And we can compare that to the data, and bang on, it agrees with what we see subsiding in galaxies. So in a nutshell, I kind of went through a lot, but let me just see if I can summarize. When we look at our universe as a whole, the data and the theory shows us that the universe, which is made up, which is a dynamical field of space-time that's expanding, and comprises of the fields of matter in our universe, is undergoing sympathetic vibrations, and these vibrations contain energy that later on coalesce to form the first stars and galaxy. Now, it's obviously what I've given you and presented to you is a kind of a simplified picture, right? And there's a lot that we still don't understand. We don't know what the dark matter is and what the dark energy is, and there's still a lot we don't know. But this basic picture that the universe really is like a music of the spheres is very compelling. And I want to kind of leave it at that and say that, you know, when Coltrane said that he wanted to understand, take music to this next level, you know, there was, it's really, I think there was a deep intuition that he had that I think was also, that transcends even today how we're even thinking about physics. And I kind of want to leave it at that. And that's my little, hopefully 10-minute presentation.
All right, that was excellent. It was a little more than 10 minutes, but I'm hoping that, and I'm not sure, Peter.
It should have been 2 hours, just to let you know.
Oh, I have no doubt. I have no doubt. That's a whole semester course you could have spent, you know, going over that. But what I want to hopefully ask Peter, if it's possible for us to go a little beyond 7, you know, so that folks will get a chance, because Brandon's going to speak, Gregg is going to speak, I'm going to speak, and I really want to give people a chance. So we actually didn't get started until about 1:45. So if that's possible, Peter, would really appreciate it. Brandon, take it away.
All right. You know, tough act to follow doesn't quite do it there. That's one of the best to ever do it, who just spoke and was able to articulate all these important ideas. Thankfully, I think the way that I think about evolution is one that is compatible with a lot of the things that we're going to be talking about here. And I'm going to use my own example. I'm going to share my screen, if that's all right, and take you through one quick example of the way that we think about evolution, that is, it connects to kind of the creative force of evolutionary biology, why it's a creative force, how it actually works, and how there are kind of themes for forces like improvisation and kind of uncertainty that underlie it. So I'll do that if that's okay. All right. So when you see, everyone can see this now. You can see this animation playing out here, right? This is kind of this animation that is kind of capturing, you know, all the kind of diversity of life. And I think this is a little bit misleading, because it's basically demonstrating kind of the process through which Homo sapiens evolved. Now, I think, you know, you're going to see, right? And I think what is misleading about this process is that evolution is not a progressive force. It's not necessarily trying to take you forward in any kind of way. Like, that's not the way it works, right? And so that kind of is a misleading thing that I think a lot of us kind of erroneously believe about the process, that it's kind of this intrinsic thing that's marching us forward. That's not true. Evolution is solving whatever problem is in front of it. And I think the challenge and the beauty, though, is this biodiversity, because a lot of the species you're seeing here kind of still exist on Earth, many of whom we predict will be here long after we will. But the question is, how do you get this type of complexity? What's under the hood? Right, as they say, how is it actually working? And as you know, right, in this modern age, right, we actually now have a picture for the way this works at the smallest scale. So this is like the largest scale. You see whole organisms and limbs and leaves and all these different things, but there's something much more provocative going on. And we'll use this example now about how proteins are evolving, right? Proteins that are all a part of this. There's millions, and they're being created and broken down every second in every cell of your body. And we'll kind of use this as an example. Now, what I tell people, one of the things I appreciate about Professor Alexander and Gregg and everybody on this, both Greggs and everybody on this call, is that I tell my students, I tell my colleagues, everybody should be a historian of your field, everybody. Right. And that goes for whether you do jazz or music. It's like, it's almost, you can learn how to play the instrument, but you're not really a musician until you've learned the history of it. And I think one of the cool things about that is once you study the history of your field, you stumble on people who are kind of like you. And you're like, I'm kind of like this person. This is kind of the person. I think one of the people in this field of evolution that I've stumbled on is somebody named John Maynard Smith. Now, John Maynard Smith is a British evolutionary biologist, and really, really brilliant and polymathic, and kind of thought broadly about a lot of different things. Different people know a different John Maynard Smith. So some of you might have heard of what game theory is. John Maynard Smith was the person that brought game theory, and that's in economics. You might have seen Beautiful Mind. Beautiful Mind was the application of game theory that won the Nobel Prize in economics. But John Maynard Smith brought that to biology. So John Maynard Smith was just broadly brilliant, and also, like me, liked to discuss things and argue over a pint of beer. He's well known for. A lot of my colleagues actually knew John Maynard Smith and were able to hang out with him. But I started reading his life, and I was like, this is the kind of scientist, not that I'm this good, but this is the way I think about things. Now, what's one of the things that John Maynard Smith is important for me that relates to this conversation? When I was in graduate school, I read this paper that came out in 1970. And don't worry about the text now at the bottom, but it's called Natural Selection and the Concept of a Protein Space. It's a short paper that came out in 1970. If you do the math, 1970, well, as of 21, it's 51 years ago, but it was 50 years ago. So I just published a 50-year reflection on this paper that came out last year, where I kind of reflected on this paper and why it was so important and what it did for so many scientists. To put this in perspective, in 2018, the Nobel Prize in Chemistry was awarded to Dr. Frances Arnold, right? One of few women to ever win the Nobel Prize in Chemistry. And in her Nobel Prize, she talked about John Maynard Smith a lot. So this single paper that I'm showing you here had this huge impact on people in the chemistry world, in biology world, in the medical world, and all these different worlds. So what was it about it? And what I did in this paper, and the way this connect, you're going to see this connect. What made this so radiant? I did a little bit of history on this paper. It turns out that this paper was a rebuttal to another paper that came out in 1969. Now, whatever. This guy, who was a very well-regarded plant biologist, wrote this paper called Natural Selection and the Complexity of the Gene. And I'll kind of get through it. But basically what this individual said is that life is too complicated to be solved by evolution. There's no way natural selection can come up with these types of solutions, right? And he came up with all these kind of crackpot calculations to demonstrate why. Note that these were both in really prestigious journals. So Salisbury comes out with this paper in 1969. Maynard Smith comes, and the way I kind of say it to myself in my lingo is he read this and was like, nah. Right, and he comes out with this paper. But here's the awesome point about it, and this is kind of something that I've taken with me. He starts off the paper with, Salisbury has argued, and doesn't mention Salisbury again for the rest of the paper. It's kind of like he doesn't even give this dude the attention. But what he does, despite being one of the most brilliant mathematical biologists ever, right, he offers this. I'm going to disprove this hyper-complicated mess with a model of protein evolution I want to discuss as best understood by analogy with a popular word game. He used a basic word game to make a profound point about the way evolution works. And what's that word game? It's one we've all played, right? You're given a word, and you have to transform it into another word, and you change one letter at a time. All right, this game has different names in different communities, and I can ask this crowd, like, which of these paths would be the winning way to get from word to the word gene, changing one letter at a time based on the rules that we know from word ladder? What would that be? Any guesses? Do we have any in the comments? Let's see. 4. Good. Okay. 4. I'm seeing some 4s. I got a bunch of 4s. Excellent. Can I hear people offer? Can one of the people who said 4 tell me why? Can Henry say why they said 4?
Yeah, because each of those words is an actual word in each step.
Love it. Right. Absolutely. So fabulous, right? All the words are meaningful words, right? Just like that. Now, what does that have to do with evolution? And why would John Maynard Smith, one of the most famous biologists ever, use this as an example to demonstrate the way evolution's working? Because what John Maynard Smith is saying is something profound. Evolution does not have to solve problems all at once. It solves problems little by little, and it kind of walks to and towards these solutions. The only thing that has to happen for evolution to explore new things and to discover new solutions and to evolve new structures, the only thing it has to do is that the steps in between have to make sense. So as long as solutions are in a pace, and we're talking about a protein, we're talking about a structure or a DNA, all the thing that has to be the case is that as it's searching, all of those things make sense. Now, what does making sense mean in biology? Well, making sense means it's functional, right? If you're talking about an enzyme that digests your food or something like that, right? It has to perform the function to digest your food. I don't know if you all have eaten or are planning on eating or whatever, but the minute you're eating, before you eat, you're going to have, right, your cells going to be cranking out these enzymes that are breaking down the sugars and the proteins, and right, in your bloodstream. Those are enzymes. In order to kind of evolve new function, the only thing that has to happen is whatever thing it's evolving into has to retain the function. Now let's compare that with some of these other ones, like this one, right? This is not really a word. That's not really a word. Now there are other words like were is certainly a word, but W-O-R-E-D is not really. Okay, so this one certainly is. So there's not really a route between here and here, even if this one is a great word. So evolution is all about identifying pathways and locating solutions. And that's actually the creative force of evolution. It's constantly searching and tinkering little by little by little, mutation by mutation by mutation. Okay, right? And so what we saw from this analogy is that John Maynard Smith went on to be one of the most famous biologists ever. And different biologists know different John Maynard Smith. I already told you about game theory. People who study the evolution of sex know John Maynard Smith. And what happened to Salisbury after this paper, right? Did Salisbury try to fight back? Well, Salisbury started publishing things like this and things like this. So Salisbury was actually a creationist and a religious the entire time, and was basically trying to hide these creationist ideas in his science. And we learned that happened, and basically he went in this direction firmly right after John Maynard Smith. The one book that Salisbury did write, though, that I must confess that I really want to read and I empathize, is the one about UFOs. I'll give him that one, right? I'll give him that one. But the point is that this was a really important idea that allows us to kind of rethink. And what we'll find, and I'll kind of end here, is that not only is this metaphorical, right, that there's always possible solutions and that evolution kind of locates these pathways, this actually applies for real with real enzymes. I have papers now where I've taken this exact structure and I've applied it, right, to actual enzymes, where instead of individual letters, these are amino acids. So to make it very, very serious, when we're thinking about things like COVID and evolution in COVID, this is exactly what's happened. You have a protein that's evolving individual mutation by individual mutation, and it's locating some solutions that are better for whatever function. And in this case, being able to infect people, just to make it very serious, to let you know that this is a real thing that we're talking about here. So, so yeah, I'll end there. I'll end the formal presentation there, but I just wanted to kind of highlight the way some of these concepts like play out in my work and kind of how we've thought about them historically. And I think the cool thing that you're going to find in the way I think about it is evolution now is becoming an information science. It's about the way information is organized, right? And I think that's the connection between the stuff that I do and the stuff that Stephon does in terms of scales, is that it's about, okay, life is charged with this problem. How do I take all this matter and organize it in a manner that makes sense to perform some kind of function? And I think that's kind of how I'm able to keep good wine in my cellar, as I keep coming up with interesting ways to describe that process. I'll stop there.
Thank you, Professor Brandon. Professor Gregg Henriques.
All right, man. Hey guys, thanks so much. Excellent stuff. You know, I've got a saying that I have: as I ride the wave of the crest of causality, I look out onto the sea of probability and back onto the sea of effect. So I feel like I'm riding some vibes here at the level of matter. And then Brandon, you're picking up the natural selection genetic cell wave here. And you ended on a really crucial point, as far as I'm concerned, which is on this information, the evolution of information processing, the evolution of complexity, the evolution of communication, these complex dynamic systems that start with the harmonious universe playing a particular tone. And then if we follow our particular trail as human beings in the cosmic coordinates, I'm all about trying to pull that together and see how that fits. Now, I'm jealous of you guys, okay? The reason I'm jealous of you guys, I got science envy, okay? Because you guys are hard sciences. And you know what I am? I'm in psychology over here. Psychology's got problems in relationship to having science envy. We talk about physics envy all the time. And so what do I mean by that? Well, you know, Stephon, hey, what do you study? I study matter, energy, maybe space and time, but we physicists know what we're talking about in relationship to the basics, right? You got quantum mechanics, general relativity, Newtonian classics, you put it together, you got something going. Then we can pop up to natural selection, genetics, and cell theory. And we biologists, hey, we have a language, thanks to Darwin, thanks to genetics and brilliant people like John Maynard Smith that actually tell us, hey, there's a frame for what life is. Schrodinger might have said, hey, we don't know what is life. It might not be easy to define with specifics, but man, you can get a circle around that thing. Now you come over to my discipline. What is psychology? All right. And that's obviously, that's my folks where we get soft, at least at one level. Our field hasn't figured out how to get consensus on what the reference is to this concept of psychology. Okay. We call it in textbooks behavior and mental process. All right. But there isn't a shared consensual understanding of a frame of reference about what we mean by behavior and mental process. And that's where my passion is, trying to figure that out. I want to figure it out because I'm a clinician. That is, I work with people in their everyday lives and the suffering that is so, well, rampant in so many different domains. How do you sit with people and the fights they have with their significant others, or the worthlessness that they feel, or the wondering about the cosmos and how they fit into it and whether they matter. And my profession is, how do you enter that world and how do you relate to folks to that level and bring a little wisdom so that they might grow and change and move in a different way. And I really do. I sort of have a feminist heart as a therapist, but I also have this kind of physicist, scientist head, and I wanted to put some pieces of the puzzle together. And that's kind of where, you know, my trajectory took me. It brought me a tree of knowledge system that says, hey, there's these different planes of existence, matter and energy, life, organized by natural selection, genetics, and cell theory. And then another jump in the information domain on a nervous system, complex active bodies, and the unique kingdom of animals that move around, make predictions about what's happening, jive with each other, like you'd see bees in a hive. That then becomes the domain of the animal. And animal behavior, in my language, is actually best, we should call that actually mind. That is, if we see that as mind, that animal behavior as mind, then we can say, oh, here's an observation. Really, behavior is what is epistemologically available to us, meaning, hey, it's how we as scientists can see what is mental from the outside. Because my discipline has this whole problem about, wait a minute, there's the outside view, sort of from the third person in, versus now we really have first person experiences, dogs, cats, And of course, people sit from the inside and they have their subjective experience of being. One of the things that made our discipline so complicated is that the subjective experience of being, trying to get that into the language of science, has always been a problem. My frame of reference is, hey, we should divide the universe up into these different scales: matter, life, mind, which is mediated by the nervous system and gives rise to behavior of animals as a whole. And then how do we understand that? Well, we can understand what the nervous system is trying to do. What it's trying to do is it's trying to detect forms, okay, and make predictions. That's what the nervous system tries to do, and anticipate what's going to happen. And then you get jolts of pleasure and pain when you anticipate and move in a good way. That's what pleasure is. And pain, which is, oh, this is bad thing coming and I can't get what I want. I believe that actually our subjective experience of being comes from pleasure and pain in that way. And then it evolves into a phenomenological experience, where my friend John Vervaeke calls it an adverbial consciousness, which is basically the witnessing function of adjectival consciousness. That's the gross experiences that we have behind our eyes. And we share those with crows and other higher animals like primates, okay? And then ultimately, what we do is, in my particular passion, where I really started on this journey, was how do we as primates start syncing up with one another intersubjectively? Before we have language, we actually have, Michael Tomasello talks about shared attention. And that shared attention started us in a particular kind of groove, okay? And then when we had that shared attention, we started using symbols and mimicry. And more than any other animal, we were engaged in cooperative synchronicities. And I argue then that once we started that symbol, there was a tipping point when we got to propositional language. Propositional language was the process where we could say, hey, this is true or false. And then you make claims about the self, about the world, about others, about the future. And then you engage in question, answer, dialogue, what I call justification. You try to justify what's right, what's wrong, what you ought to do, and you engage in social processes of justification. Once we as primates were able to start to justify and build ourselves, all of a sudden, a whole new world opened up. And that has all sorts of different ramifications and implications. And actually, with that whole new world, I'm going to pass it on over to Gregg Thomas.
Thank you very much, Professor Gregg. I appreciate that. And I'm going to try to be as succinct as I can so we can start to have conversation. But I'm going to take off from where you just left off. Excuse me. So your justification system hypothesis. Excuse me. So you have widespread justifications, reasons, and within networks of people, they become cultural agreements. And then based on those agreements, we think and behave in certain ways in accord with those agreements. But let's go deeper. So justifications, as Gregg said, came into play with the advent of language. So let's linger on language. A basic function of language is what? Communication. So communication among agents in an environment or an arena. Communication is actually more fundamental than human language, okay? As we know, what we call communication, having signals received and interpreted by a recipient, occurs also at the subatomic and atomic levels and via biochemistry. Those communication is happening there too. And what is it communicating? As Brandon mentioned, information. Gregg has a lot on how information fits into his TOK system also, and his UTOK system. So in humans, information becomes knowledge, and we can frame knowledge as ways or styles of knowing. Now, our guest next week, one of our two guests, John Vervaeke, Gregg has already mentioned him. The other guest is Stephen McIntosh next Monday. He talks about knowing or styles of knowing in 4 ways. Propositional knowing, where you make statements in writing or speech. Procedural knowing, which is how you do things. Perspectival knowing, in which you see through varying frames to determine or realize the salience or relevance of experience. And then participatory knowing, in which our actual engagement with other beings brings learning. So communication is a way we transmit information into knowledge, and language is an engine of communication through symbols. Culture involves communication and knowing, and language is a symbolic vehicle through which culture evolves. So let's swing even deeper. What is the creative engine of language? Well, there's literal and figurative language, and denotative and connotative meaning. So I contend that the interplay of these is a creative engine driving culture also. So words in their basic sense, without metaphor or allegory, are literal. Those who believe that the world was created in 6 days, as it says in the book of Genesis, they have a literal interpretation. Relatedly, denotative meaning is a strict confined definition. But the creative juice of language really explodes with figurative language, with poetry and figures of speech that make comparisons beyond the literal and the denotative. Connotative language involves the emotional association of a word or phrase, often positive or negative. Emotions are the concepts we use that point to feelings, that point to some of those basic pain, pleasure, sensations that Gregg referred to. Metaphors, which has come up several times, as has analogies tonight, are figures of speech that compare one thing to another for poetic and rhetorical effect. For example, in As You Like It, Shakespeare wrote, "All the world's a stage and all the men and women are merely players." So such a metaphor extends our perspectival knowing through poetic propositions. And Shakespeare's procedural mastery as a wordsmith and playwright affords us the opportunity to participate in the aesthetic experience. Analogies also show how things are alike. That was one of the things that that Brandon talked about with John Maynard Smith, that master analogy that he gave. So analogies show how things are alike, but it also gives some explanation. In the Jazz of Physics that Stephon mentioned early on, he used music and in his presentation as the analogy to relate the quantum world to the superstructure of the universe. In a session on a class that Professor Stephon and Professor Brandon were guests of mine at Jazz at Lincoln Center, I taught a course called The Art and Science of Improvisation. And I posed a question to them and asked them to come present. And the question was, does life and the universe improvise? And so jazz improvisation was used as an analogy to explain processes at the quantum and biological levels of reality. Okay, early on, the young lady in the video, she said, "Oh, these electrons, they have commitment issues. You know, they don't know if they want to be a wave or a particle." That's an analogy. That's a metaphor, you know? So let me use the cultural tool of language to connect each of the disciplines we've spoken about to each other, okay? So for me, electrons as particle or waves points to a fundamental dynamic of the many and the one. A particle is a unit. A wave are units in flow, in spiraling movement. Each individual watching this now or another time has an individual foot and fingerprint. That's all your own, a physical representation of your uniqueness. Yet we are all parts of waves or networks of relationships, family, friends, generations, ethnicities, nationalities. You could look at the US motto, e pluribus unum, out of many one, from this perspective. So now there's a word that hasn't come up that could be discussed, and I'm going to bring it up from physics. So at the level of physics, the second law of thermodynamics applies to closed systems. We're talking about entropy. So in closed systems, disorder or randomness, or what some call chaos, increases over time. But at the level of life, life says, to hell with entropy. That's what life says and does, okay? So life moves, metabolizes, self-organizes, passes on traits and patterns from one generation to the next, evolves, and engages in complex, nonlinear networks of relationships at fractal scales of being. Life is, as James Carse puts it, an infinite game. Life intends to stay for the duration, baby, which is why creativity and improvisation are fundamentals to the expression of life at all scales. And as an extension of life, mind does the same, as does culture at higher levels of complexity. All of this is in service of life, living, what scientist Andreas Weber calls aliveness and enlivenment. So that's my attempt to bring it all together.
All right. Thanks for making us feel alive. Excellent.
All right. So, Stephon, Brandon, you have any comments on what Gregg or I said? The two of you kind of have that simpatico already. Can we get a conversation going where you can riff on what we've said?
I'll let Dr. Brandon go first.
You gotta unmute yourself, man.
Mhm.
Sorry about that.
That's
I
all
think
right.
there's a I think there's a lot, and I think what I'll talk about there is, I mean, the way we structured the conversation um is, I mean, you can kind of think about that, right, from the very small, the micro, and then the way the mind works in particular as this complicated instrument. So from the way the basics of matter that have nothing to do with living things at all, really. There's nothing about living things that what Stephon thinks about. Not only does the matter that Stephon thinks about, the ideas that Stephon thinks about carefully have nothing to do with people. They were here well before people. They'll be here long after people. And I think as we've kind of proceeded in the conversation, these further and further kind of organization of as a further and further more refined kind of organization and representation of this matter. And so a living thing and the origin of life is just this process of taking matter and kind of organizing it, like you said, pushing back against entropy, which is really a good functional definition for what a living thing is, and then organizing it into, right, this thing called behavior, which, I mean, frankly, is as absurd a step statistically as the origin of life at all. Then, right, the origin of consciousness is really as absurd with regards to just the notion, how it happened and why it happened, and how kind of incomprehensible it is. How rare it is. Consciousness is very, 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 very rare in the one place that we found it. And then now, of course, we're attempting to kind of recreate it, which is what a lot of industry is about now. So I find that, and then culture, right, which is something even more absurd, right? The notion that not only does this collection of matter and electrons zipping around with charges and polarities and all the other weird, super weird, trippy, acidy stuff that Professor Alexander studies. Not only is that, not only do you have to find a way for that to organize itself, it has to learn how to think about itself and then kind of generate this wide cloud of things we call culture. So I think I find that kind of flow of information very, very interesting, and I find that kind of as a theme for the way everyone has talked about things. I can kind of kick it off there, and then kind of talk about we can talk about other parallels we're seeing between these different scales of interaction and contemplation.
Yeah, that's really, I'll just echo that. For me, the frequency of information vibration across those different matter, life, mind, and culture, well, that really jazzes for me. So, I appreciate you highlighting that.
Mm-hmm. Well, and then, culture, which here's what's amazing, right? You talked about metaphor. Gregg made Gregg with one G, Gregg. That's what.
Yeah, that's cool.
Gregg talked about culture, right? And what's powerful and fascinating is that, I used analogy and John Maynard Smith used analogy to reveal fundamentals. So we use culture to tell ourselves about things going back down the other direction. Stephon has a best-selling book called The Jazz of Physics, where he used jazz to explain some fundamental things about the way the universe is vibrating, which has, again, nothing to do with people playing instruments. That's just the universe itself. So I think culture really is in some ways the most, even though it's the most sophisticated, in many ways it's the one that has the power to say the most about all of them. Right. So I find that I find that also to be a very interesting and powerful concept that emerged from this.
Yeah.
Yeah. So
Let me riff on that. No pun intended.
that's the point.
Since I'm no big pun.
Yeah.
Like that pun too.
I caught that. I don't know if everybody else did.
Boom.
No, you're dropping bombs there. Like that one too. Who was the drummer that invented dropping bombs at Minton's Playhouse?
That was Kenny Clark.
Yeah.
He was famous for playing and then dropping bombs in style called bebop. Yeah.
Right, and that's a cultural thing because that was actually a mistake. And so you got now jazz drummers going to the top schools and halls of music theory, learn how to drop bombs, and it happened, at Minton's Playhouse. Right.
That's right.
As a mistake, and that's exactly what I think Brandon was talking about, which are these when you think about evolution, like these kind of like mistakes, and then they become functional, and if not, it doesn't stick, right? And so that interesting kind of like reverberations. I mean, one of the big let me put on some elephants, expose some elephants in the room now. If we take some of these analogies, these metaphors, especially like we think about culture, like the emergence of culture now that these complex, as Gregg with 2 G's talk about now, these systems, humans that can now communicate and transmit information, and now you have this informational processing conglomerate of beings.
Yep.
And then you have culture now, and now that becomes its own informational processing, and then I can use a metaphor and say, well, the universe that doesn't seem to care about people because it's an entire universe. There are some semblances of culture. Does the universe have culture?
Well,
are there aspects of culture that the universe can have?
Yeah, I mean, if you look at culture as a process, there are certain relational processes that you can analogize to that. This is one of the reasons why Dwayne Elgin is a futurist and writer who talks about, if we as human beings think of the universe and the cosmos as dead matter, therefore we can then exploit it, extract from it, because it's dead anyway. But if we think of the universe and the cosmos as alive, just like we know nature is alive, and we're part of nature, and we're part of the universe, that's what we come from with star stuff, then our whole orientation to life and reality can change, which is why I would posit the thesis that the universe is alive. There's movement, there's processes that we can point to and say they're analogies to what living things are. Now, it's not live in the biological sense, I understand, but just like in this course I taught on cultural intelligence, where you and Gregg Double G were my guests for my last class, you talked about how you could look at what you call proto-consciousness. There are certain things that you can point to early on that you can then say are similar in the way they function to what we call consciousness and culture.
But okay, I want to push back, but I want to push it back to Gregg Double G and Brandon to answer the following question.
Cool.
Okay, the question, as you said, if we're gonna go there and say, well, not even, you can't get away with just saying not in the biological sense, because you use the word alive, so now I got to go there. Okay. So here's where I'm gonna go.
Okay.
Well, so what Brandon would say is that, well, if you look at like life on Earth and you look at everything, there still is a biosphere, meaning that, you know, Earth is protected by magnetic fields and like crazy stuff out there, cosmic radiation, things that will obliterate any type of, you know, carbon-based thing that we could imagine. And it seems that, you know, a lot of more conservative, like astrobiologists would say, our biosphere, planet Earth, is, they call it rare Earth, is rare. Now, I don't personally believe that, but that's just me now speaking as a person. But we have to, I want to kind of go there. I want to now say, well, if we were to push this, I want to push it now back on maybe Brandon to riff maybe a little bit, is how will you reconcile my, you know, what I just said there, that there is this biosphere, and then there's this vast, I wonder, because people really do think like in a more material, like there's outer space, it's cold, dark, you know, there's all this electrons flying out there. We just want to harness all the energy we can get, and you know, and that's it. We're in the biosphere.
You gotta take yourself off mute, Brandon.
What's your question, Stephon?
It's not more a question. It's more of like it's a pseudo question. It's more, I don't know what the question is. I mean, it's more to say that since this idea that maybe can we extend the notion that there's something about life that can go beyond the biosphere? Okay. Because we know that the biosphere does exist. It's called planet Earth, and then beyond that, though, it seems to be this inhospitable place. Now, but there seems to be an intelligence, and I don't want to use this word in any other way than as you said, is that the laws of nature and entropy seems to want to find functional spaces for proteins to be in these functional spaces, right? So somehow the universe ended up, at least in its corner, to do what it's doing, and then to create culture. So what is it doing? I'm saying it to both you and Greg.
Yeah, you can go.
Yeah, okay. So a couple things here. For me, I want to emphasize both continuity and discontinuity. And that's really that tree of knowledge thing's really about continuity and discontinuity. So I want to look back into the universe, and when I'm jiving with it in a particular way, I want to see some degrees of continuity. I want to open myself up and not just see the dead universe, but maybe see it as a whole in a particular kind of way that's interconnected, has some complex relation, certainly has our place in it, at least in the macro scheme, maybe other forms of life. You showed the picture look like almost like a nervous system. So there definitely are ways, metaphors, and opening us up to see patterns so that we're not closed down in relation, okay? At the same time, we don't want to become gullible, right? And when we use the word life in biology and ask, like Schrodinger did, what is life? A cell looks very different than even a protein molecule, okay? And sure as hell looks different than a star in terms of the complex dynamic organization of it. So if our term is life for that, I want to preserve that, and that's discontinuous. That's why we have biologists, and they speak different language than physicists. You can't reduce biology to chemistry in my mind.
Yeah.
You know, the information store, the complex arrangement, the natural selection, building complexity, all that stuff requires a totally different language. And then for me, you know, you layer a whole nother level of complexity. You get that nervous system yoking the body together. You get the behavior of the animal as a whole, perceiving, sensing, moving around. And that's different. People will say, hey, I think cells are conscious. And yeah, I think they process information, they respond, they move towards it. But as a psychologist, I'm like, well, I don't know about that.
But Stephon, wasn't that the very, wasn't that the very thing that you said was like proto-consciousness?
Yep.
Wasn't it the cell that you had mentioned in that class?
I was more referring to, that's right. I was referring to this, some of the more current ideas. There are many different words for this, but now the current sort of hot word is panpsychism, but it is now grounded where some of the most conservative neurobiologists, like Christoph Koch, for example, and Tonini, who are experimental, you know, top-notch people, are now starting to say there must be some, you know, kernel of truth this idea of panpsychism. And
Right.
It could be a glue. It could be a glue.
Yeah, they have, I mean, integrated information theory, which gives a way to understand the way information is integrated, processed, differentiated, and then you demonstrate functional awareness. And then there's a measure of that integration, differentiation, and functional awareness. Now, myself, and the way I use language, I don't like their term consciousness for some of that. Like a photodiode can be conscious. It's very simple.
Exactly. Yeah, I agree with that.
It's like, no, that's very different than what we mean, at least us humans. When I say I'm conscious and then I went to sleep and then I was unconscious and I got back up again, I don't know how a photodiode loses consciousness, even though I could still see how it processes information. So, I mean, that gets into some, kind of what are the metaphysics of consciousness and all that. And people are going to bring different languages and have different reference points to that. But,
Yeah, I can definitely speak a little bit to that point from the physics perspective and why we are forced to confront that that question. So it's because when we in quantum mechanics, which again quantum mechanics could make, meaning I can solve the relativistic version of quantum mechanics, so-called quantum electrodynamics.
Sure.
The equations and calculate I can basically calculate there's a particle called a muon. It couldn't happen for the muon, a heavier version of the electron, and it has a dipole, an electric dipole moment, and I can calculate basically how it processes in real time with 10 orders of magnitude from the zero in terms of this value, okay, from this orbital motion, 10 decimal. So you have 10, it calculates 10 to 1, 2, 3 point, da, da, da. And then you go measure this thing and it fluctuates by the 11th decimal points.
Yep.
That's the power of quantum mechanics, right? So that's how serious like the theory is. However, what it's saying about reality is absurd. So with the baby in the bathwater, because it will make these predictions, but then it requires basically it requires some kind of observer. Not requires. It turns out that there is this measurement problem in quantum mechanics that basically says if you're not looking, that's what stuff happens. But if you look, you're screwed. So for quantum mechanics, it seems that one of the things I had to do for my second book was to I wanted to do justice to this, and I read the foundational book. Man, it was by John von Neumann, who was the father of the modern computer, but also he also wrote a book called The Mathematical Foundations of Quantum Mechanics, which was basically the book that everybody went to. Yeah. So where he proved quantum mechanics, it's like over 200 pages. It's a pure math book. And I really went through as best as I could with my abilities, because I'm not a mathematician. I mean, I'm a mathematical physicist, and he in that book proved in this book that if you go through this reasoning, like consciousness is a thing that has to register the measurement. All right. Like the only way out is this. And so the whole idea of panpsychism, it seems to be the only logical way out of it, in the sense that if the quantum particle itself has an ability of self-observation, right? Now the self-observation, again, its state of consciousness, quote unquote, is a very minimalistic thing, meaning that its state probably is not a state of consciousness it's very proto. It's very like, I have charge, right, and I can see my charge kind of thing. It's a very I'm just shocked to exist. Because that's
well, obviously when we're talking about human beings, we're talking about a self-reflective awareness and an ability to go backwards and forwards in time in our mind. I mean, we're talking about, when you're talking about the culture plane of existence that Gregg talks about, you're talking about another order of complexity that human beings, therefore, the way that we manifest and use our consciousness is going to be, orders of magnitude, to use one of your terms, Stephon, beyond that. I mean, obviously.
What I'm saying, I was just adding to just address Gregg's thing, is that the idea of proto-consciousness is, just to make sure I'm clear, is that an electron, the same way like the electric charge or the spin of the electron and its mass are intrinsic to the nature of the electron. It can't be reduced. What they're saying is that this idea of like the idea of panpsychism or whatever word it is that the electron has an internal experience that is only in reference to its principal qualities.
Yeah.
But you can have organizational properties that become more. So then I can have jellyfish consciousness, or it gets more and more complex.
Right.
But you know, a single elementary particle has built in it the same way it has charge and mass. This ability it has an external reference to space-time, but also internal to its.
So it has some semblance of subjectivity. What Andreas Weber, who I mentioned earlier, talks about.
Very minimal. It's
very minimal. It is very minimal. Yes, true, but it's still there. There is some type of subjectivity. It's not just, there's a first person feeling level. That's what Andreas Weber talks about. The feeling level is the fundamental thing. Feeling, some sense of a core self that feels and is attracted or repelled by things. And that's like a fundamental unit of what we talk about being alive, aliveness, you know? So I think, Peter, that we should, at this point, bring some other folks in to comment, reflect, ask a question, or, you know, but I want to get some of these folks in here who've been patient with us and been sticking with us. And I want to thank them for that and give them a chance to swing with us.
Beautiful. So we're at the top of the hour. Anybody have a hard stop?
I don't.
Yeah, so maybe 15, 20 minutes. Is that good for Q&A? Okay, because we reached the schedule time, but we're happy to stay a little bit over.
Thanks, Peter.
Let's tag in Hayden. You had a question. And start throwing your question in the chat right now, and I'll call you.
Yeah, thanks so much for calling me in here. I'm going to pull it up real quick. My question is, how does the evolutionary emergence of consciousness itself, particularly like human reflective consciousness, affect the process of evolution itself, or potentially affect the process of evolution, specifically through the emergence of human agency as a co-creator with life's own evolutionary process? Another way I could say that is, how does human intentionality and imagination affect and potentially direct the evolutionary process of becoming itself?
Now that's a Brandon question, but I do want to just give a quick cultural response and hand it over to the master who will go further. But there's a dynamic, and this is I'm sure Brandon can confirm or deny this, that culture actually impacts our genetics. In other words, there is over time social learning that goes on and behavioral learning that happens where culture then impacts the genetic development of species. Okay, there's probably more precise ways of putting that, but in my reading of the literature, that is something that occurs. So please take it from there, Brandon.
Yeah, I mean, so I think that's a powerful question. The last part you said, the evolutionary process of becoming. I'm gonna have to that one I'm not clear about, but in terms of human intentionality, I think the greatest human intentionality is the greatest evolutionary force we've ever seen already, by far. And I think the easiest place to see that is in artificial selection, right? Is in what agriculture is, and in what the domestication of animals is, and the way we've kind of like look at what we've done to the planet. So the debate over the Anthropocene really kind of lives here. It's the human beings have done all of these tremendous things to try to engineer life to work in our favor. So what I'm saying is, yeah, human intentionality has these profound influences, not only for how we evolve, but how all other species evolve, or many other species evolve. So I think there's that. So I think, and so there's that, number one. Number two, there's the effect of intentionality on what we're doing with ourselves. And now we actually have the tools to tinker with our genomes successfully and effectively. And that is where that whole debate lives about whether we should be doing that. Would you introduce a mutation of some kind for a hair color that you think is cute? right, you actually are influencing generations moving forward. So we actually have the ability to do that. And I think thirdly, is the artificial realm. I've gone to artificial life. We actually can kind of engineer completely artificial instruments and matter with these kind of evolving capacities, right? And I think so the jury's out in terms of what that's going to become. When we evolve robots that can evolve to be able to perform functions better, it'll be really, really exciting. So I think, yeah, briefly, yeah, I mean, I think consciousness and intentionality has already been a huge force of evolution, and will continue to be.
Excellent. Yeah, so if I pick up on that just a bit, Greg Thomas pointed me to a blog called Conscious Evolution. And basically, so if we think about our intentionality, there's one level intentionality. Hey, we wake up, we start talking to each other, we realize we're going to die, we build myths of how the world works. Okay. I think we're actually at the 21st century at a potential another level of awakening, so that we actually can situate ourselves in the cosmic coordinates and then maybe collectively start making choices. I see Lee Beaumont here. He created, based on some of my work, a level 5 research idea. Level 5 is the thing that comes after culture. And one of the things that we see, if you follow the tree of knowledge logic, every jump comes with an information processing communication network. So you get that into genetics and cells, you get it into animals' nervous system, you get it into humans talking. Well, the artificial world that we built in the internet and computers and artificial intelligence, well, that sets us up for a digital virtual jump that I think is happening right now and making us fairly funky. So for me, the issue is, hey, can we wake up? Can we choose where we are? Can we pay attention to how technology is evolving and do so wisely? So hopefully we'll consciously evolved with intent towards wisdom. That's what my hope is. All right. Next question, maybe, Peter, if we have another question.
All right. Christian Sawyer, you had a question.
I did have a question. Let me scroll up a second. There we go. Improvisation needs some, quote, constant, or at least I'm proposing this, to orient around if it's going to be meaningfully called improvisation, as well as some amount of entropy, which allows for new possibilities. So can we say that the musicality of life is an imminent relationship between, speaking very abstractly, or some kind of pure entropy and some type of pure like teleology that's grounding everything somehow? And some of the things that sparked this question are like listening to John Coltrane, listening to like Om, and it's like just going everywhere, but there's a felt sense of like deep groundedness, like just like this at the same time. And that relationship feels like it's a big part of jazz to me.
Let me just very quickly say that often in jazz, you have a complex dynamic going on where the rhythm section, the bass, drums, and piano, they're the fundamental unit, the rhythm section, because it's the rhythm that defines what any music is. So if you have a particular melody played in a reggae rhythm, it's a reggae version. Jazz, the fundamental rhythm is swing, right? So usually you have a situation where you have 1 to 2, if not all 3 members of the rhythm section are holding down some consistent patterns. So you have the drums riding the cymbal, you have the bass player walking, on a 4/4, being the boom, 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 and the drummer along with him or her, and the piano player is doing what they call comping, complementing, accompanying, where these jabs of chords, So that's more of a looser type of thing. Then you have the most loose, which is the improvisation. The person who is soloing is improvising on the song, the melody, on the rhythm and the groove, the mood, the chord changes or the harmonies. So the improviser is using all of those elements to create their own aesthetic statement, okay? What makes jazz so beautiful oftentimes is that you'll find that whereas the bass player is holding it down, the drummer may be doing stuff that's not just straight keeping time, but accenting and doing different things all around it. Or you might find the bass player doing the same thing as the drummer keeps it down. So there's usually some type of focal point that keeps the basic dynamic, rhythmic dynamic moving forward. And then around that is the improvisation and the variety. So the kind of dynamic that you're talking about, Christian, is really fundamental to jazz. I hope that answers at least part of your question.
Yeah, and I think the other part was about that's a great, because laying the foundations there. Christian, I thought that analogy was perfect for the way we think about biology. So I think, right, one of the things about like the tree of life, right, that is so absurd, and the reason why it is so fascinating is from replicating microbes in extreme environments to Homo sapien to, all have fundamentally the same set of rules at work. Fundamentally, I mean, it's kind of shocking how for all of the vast differences, and there are vast differences, right? It really is kind of one set of rules that imply one common ancestor for all the living things. In fact, even things that are not living, like viruses, still borrow their information means. It's either RNA or DNA in some combination. So even things that are not themselves living kind of borrow our pivots around this fundamental scaffolding set, the same way Gregg just mentioned with jazz and the same way you outlined. So I think that analogy of musicality in life is one that I think works.
Yeah, and actually it works in mind too. If you look at the fundamental way in which the nervous system works as a predictive processor, it's really tracking chaos on the one hand. So it's going to make flexible predictions, and then it's going to try to narrow down what it can count on. So it's this chaos versus order. And then it's riding that balance between chaos and order in a flexible and adaptive way. That's how you get a lot of negentropic build, is on that dialectic between, hey, holding the order and exploring the chaos and finding that balance in between.
Kind of a dynamic equilibrium.
Yeah, I mean, it's interesting. I think what Christian's articulated was very on point. Especially when it relates to how, like, kind of the argument I was trying to make in the Jazz of Physics about can we think about the universe as an improvisational system? I mean, the idea there was because if you think about the kind of improvisation Gregg talks about or is spoken about in the context of tree of life and in biological, microbiology, molecular biological systems, at least there's some notion of agency. There's something doing the improvisation. But what does it mean for the universe if I say the universe is improvising its own structure? The universe, there's nothing outside the universe, right? Because it contains all by definition. And that which is inside the universe is also part of the universe. Right. So what is it? What when the universe is starting from the structuralist state, and what's actually really interesting, actually, the really reason why I thought what Christian said was brilliant is this idea, and this goes back to Murray, right?
Albert Murray,
one of Gregg's mentor, one of the great minds of our last century, who I believe was behind Jazz at Lincoln Center, and
that's right,
mentor Wynton Marsalis, and was the idea of entropy, that what the blues, the hero in the blues. Gregg had me read that book for my book, The Hero in the Blues, which is what the bluesman is doing is fighting against entropy, right? It's creating beauty and structure in a life that for African Americans full of chaos and all these other things. And he talks about this entropy, and that the blues basically is a way of creating elegance and swap, all these things, right? Swing, the concept of swing, like the sophistication of swing. Duke Ellington, right behind you, that's what it was about. It don't mean a thing if you ain't got that swing. So the thing that I find really interesting here is what is it? The universe actually has, there's actually a what is the fundamental problem in cosmology? The fundamental problem in cosmology, I'm talking about physical cosmology, I'm talking about precision cosmology, is what we call the entropy problem. It's a statement that if we believe the second law of thermodynamics, that if a closed system, and the universe is a closed system, it is universe, evolves in time or changes in time, the entropy will change, the entropy will grow. Which means that in the past, the entropy must have been very small in the universe. If the entropy was very small, that means that the universe was an ordered state relative to what it is today. How did it get that way? So from a more mathematical perspective, it becomes a big question mark, and is the reason why this year the Nobel Prize was given to Roger Penrose. So if you want to understand why Roger Penrose got the Nobel Prize this year in physics for the black hole, the Penrose-Hawking singularity theorem, it's a mathematical.
Last year to 2020?
Well, yeah, I'm sorry, 2020, yeah.
That's right.
Well, we're a month in, I'm still,
That's all right.
Penrose got that because the corollary of that theorem, that mathematical theorem, right, actually has a loophole, and it's that problem. So where am I going with it? If the universe, how could the universe improvise and create what it has if it didn't have a state space of uncertainty, which is in a lot of ways the definition of entropy. Right? If everything was completely certain, there's no entropy. So improvisation does require, a combination, a play of, as you said, a focal point, a structure within which to explore, but also a lot of uncertainty as well, or possibilities, for lack of a better word. So anyway, I didn't answer any question. I just want to point out that actually a big problem in cosmology is this problem of entropy. That's a big one. That's a hard one.
Peter, were there any questions that were written instead of, that somebody wanted you to read? Maybe we can get one of those.
There's not many questions left in the chat, but we'll call on Josh Field, okay. And this will be probably
actually, Josh, it does say to read that, please.
Yeah, I was privately messaging him, and I coaxed him to read it for probably going to be clarification regarding it. So Josh, you're up.
Yeah. So I think I'll kind of frame my question differently to how I said it, in the context of kind of the current events of multiple self-organizing collective intelligences. I'm curious, and I haven't looked into the level 5 research center things yet, so there might be some information there, but I'm curious what you see being the overlap between this emerging new level, I suppose, and the self-organizing collective intelligences, and what it looks like for us to actually experiment and kind of explore this new territory in the context of maybe steering the collectives, and how that might play into like game B notions of the transition. Cheers.
Great. So I can riff off of that for a little bit. One thing I'll say is the STOA. Okay. And what I mean by that is, I think right now we want to be consciously aware that the infrastructure of the 20th century is going to evolve. And the question is how. And we're seeing a lot of vulnerabilities. We're seeing a lot of potentials. And then fundamentally, that question is, can we, transform into something that allows us to realize our potential? Like, I don't feel like we're realizing our psychological, relational, social soul potential. I'll say that. Okay. I mean, that a lot of people, relative to our potential power, I feel like there are a lot of people that feel alienated and disgruntled. And you look at the opioid crisis and suicide and a lot of different stuff relative to what we could be connecting around. So no matter what, you know, you look out in 10, 20 years, I think what you're seeing is a horizon, a huge amount of change. On a good day, I'll wake up and say, oh my gosh, there's beautiful people out there like Stephon, seeing unbelievably cool jazz physics, right? We can come together, we can do all sorts of great stuff. I then also look around and see other things that are not good indicators, okay? Our faith in our institutions, the unbelievable changes that happen with an unbelievable rapidity, the stacked and thin feeling of our culture relative to the magnitude of if it sort of topples down. So those are some of the anxieties that I have. And so for me, what level 5 fundamentally is about waking up, okay, and looking around, seeing what has been glorious, maybe, but also really costly in this whole Anthropocene, seeing how we're treating Mother Earth, seeing how we're relating to each other, and then really asking questions. Well, what is wise living? How can we live our best lives? And maybe more importantly, how can we be good ancestors? And how can we come together and make sure we're being that? And I don't think we're hitting optimal bars along those lines. And therefore, there's a lot of work for us to do.
What a wonderful note to end on. I want to thank, of course, my co-facilitator and co-curator, Gregg Henriques, and also to Dr. Brandon and Ogbunu, Ogbunu, and Dr. Stephon Alexander, my man. I want to thank you both for joining us, for riffing and swinging with us. And I want to thank all of you who stayed with us, who put notes in the chat, who, you know, just created a receptive, embracing field for us to do our thing in. So thank you. I definitely appreciate it. And of course, Peter Lindbergh wouldn't happen at all without you, man. So
amen. And thank you, Gregg. Thank you for all you did.
Thank you, Gregg.
Absolutely.
Thank you all. Thank you, Peter. Thank you, Gregg.
Thank you all. Had a blast.
All right. Thanks, everyone. Have a good night.
All right, guys. Take care.